Okay, well I couldn't make that work, but here we are. I've just put it here. So we still got our 1 force Newton, and we've got our 0.1 displacement. So let's move on back to our spring thing here. Let's take the 250 gram mass. Whoops, crap. Whoops. Worked. And if we let it go from here, it'll bounce like a bugger, right? No problem. You'll notice it slows down a bit as well. The amplitude is decreasing. Interesting. That's because of friction, and after a while, the amplitude will get down to 0. But what we notice here, okay, is for 250 grams, which is basically 0.25 kilograms, okay, so mass times gravity will be, well, let me see, 0.25 times 10 is 2.5 newtons. So for 2.5 newtons, let's write that down real fast on our graph. Okay, 2.5, we have got a displacement now of, 0.25 meters. So let's stick that on our graph too. 2.5 newtons gives us a value of 0.25 meters. Boom. And if we did that for a bunch of masses, which you're going to do in class, we should get something that looks pretty straight. Okay? Now, what happens in class though is we don't have a nice line straight away, and this is important to work out when you're gathering data. If you have the force and the displacement, and you end up graphing your points, they won't be perfectly in a line. It's up to you, or Excel, to draw a line of best fit through those points. Now our theory tells us that it's a straight line, because F equals KX, right? Now when you've drawn your line through there, this is what your job is. You've got to choose a point on the line, and another point on the line. Now that is not meaning you choose 2 points, right? That you took as values. You choose 2 new points on your line. You work out a y value for this one. You work out a y value for that one. Okay? The difference in them, let's call this y2 and y1. Okay? And there'll be an x value, x1 for this one, and x1 for this one. Okay? Once you've done that, you should know from maths that the gradient, okay, in this case that we call it the spring constant, is equal to the difference in the y's over the difference in the x's. And what that ends up giving us in this case, well, let's check it out. We've got equal to y2 minus y1, 1.5 over x2 minus x1. 0.15. 1.5 divided by 0.15 is 10 newtons per meter. That is the spring constant value for the spring we just saw. Now for whatever spring you've used in class, okay, let's go back for a second and look at our thing from last time. Okay, we set up, this is from the notes before, we set up this table. So if you have a certain spring mass system here, you work out the time, the period, the angular frequency squared for that mass, you actually have to do a new experiment that's not bobbing up and down like this one. You have to do an experiment now that we just saw to find the gradient K to put it into this column here. Okay, so it's like the big box is like one experiment, and this is a new experiment. So for 3 different masses, okay, you'll find 3 different K values, okay, one, and remember that's newtons per meter, okay. Once you've got that, we can finally test that formula that we had. Let's go up and check it out. Here it is. The big question is, the zillion-dollar question, does K on M equal negative omega squared for you? And the way you find that out is to do it. Have fun. Go for it. Hey guys, how you doing? We're back again for another exciting episode of springs and spring constants and stuff. Okay, so we just worked out the connection between the angular frequency and the mass and the spring stiffness. And now we're halfway through a lab to measure to make sure that our formula is actually true. Remember, the formula was, let me see if I can remember it, is K over M is equal to negative omega squared. Now we know that if we change the mass on our little spring system, something's going to be different about the angular velocity. Okay? And if we change the spring stiffness, it's also going to affect this. So we've worked out values for a certain mass. We've worked out the angular velocity squared, but we don't really know yet what our K value is for this spring that we've got. And that's what we're going to work out now, and I'm going to show you a demonstration of how we can actually work this out. By the way, the tunes in the background are an Australian fellow called John Butler. John Butler Trio, hot stuff, great tunes. I hope he doesn't mind me playing it in the background, because you should all go out and buy it. Okay, now here's an example of some springs. Now we don't really know anything about these springs yet, but we've got a bunch of masses as well, okay? So if we take a 100-gram mass and stick it on that spring, it used to have a rest position here, but now if I let it go, oh, there it goes. It's going to stretch. Now I'm just going to try and stop it at a certain point. Right. This is the rest position of our mass, because the upward force from the spring, okay, is balancing the downward mass and gravity force of the mass. Okay? Now, we don't really know what value of K this spring has, but let's have a look. If I put on 100 grams, I've moved this guy from the rest position about 10 centimeters. Okay, so 100 grams has moved 10 centimeters. So let's think about what that could mean for the spring constant. Okay, if I was to draw a graph of this, let's think about it. I'll draw one here just for kicks. I don't know if this is going to work, but we'll try it. So 0.1 kilograms, 100 grams, right? So this is the force, and this is the displacement. Oh, and I made a mistake already, because the force is not 0.1 kilograms, okay? Because force equals mass times the gravitational constant, which is 9.8. Let's make it 10 for the moment, right? So 0.1 grams, kilograms rather, well, mass is 0.1, all right? And gravity is 10, we end up with a force equal to 1 Newton. So, for 1 Newton worth of force on this spring, spring number 1, okay, 1 Newton of force stretches it 0.1 meters. We're cool with that? So let's take this, whoops, let's try and sort that out. Okay, we want to play with this without losing our ink layer. Oh, we lost the ink layer. Isn't that just grand? I wonder where it went. Wonder how I get it back. I got no idea. Let me see if I can find out.